Good morning and welcome to webinar 16 of the Powerful Knowledge series. My name is Ian Mosley and today we're going to be talking all about the analog control of power converters. Normally we're joined online by Jose. He had some issues with his video feed today, so fear not, Jose is still there. He's going to be in the background though, managing the chat questions and polls side of things. Hopefully we'll have him back online for the next webinar next week. Hopefully you've joined some of our webinars before. You'll know how these work, but if this is your first one, these last about 1 hour and we have a Q&A session at the end. We like to engage with you guys as much as we can. So if you look on the right hand side of your screen, you should hopefully see a chat box. So please put any chat in there. Anything, if you're having problems, Jose will be able to deal with those hopefully whilst I'm presenting today. Or if you have any comments, that sort of stuff, please do put that in the chat box. For our Q&A session at the end of today's presentation, we will be issuing the questions box. So please do type your questions in as we go through the webinar today, and we'll do our best to cover those in as much depth as we can at the end of the webinar. Also, we'll be issuing, or Jose will be issuing, some polls throughout the webinar just to give us an understanding on the background of you in the audience today and whether the level of the content we're presenting today is appropriate and hopefully useful. So please engage with those polls as we go. I think that's most of the intro. I will just dive straight into my presentation. So, as I said, this is webinar number 16. We've covered lots of subjects prior to this, and today we're focusing on control and control theory for power converters. Control theory is a huge subject, and hopefully you can appreciate in an hour what we're going to attempt to do is really give you a high-level overview and some specific examples of how to go about designing closed-loop control for these power converters. Well, let me just there we go. Okay, so I thought I would, again, similar to last time, if there are 3 things for you to take away from the webinar today, I thought I'd list out what I think they should be. Firstly, I think it's very important to understand a methodology that can be used to design closed-loop control in power converters. If you've tried to do this in the past without a methodology, you'll appreciate that it can be quite a frustrating thing to do. So it's good to have a proper methodology that sits behind that you can work through to design your stable system. So that's what we're going to talk about today. Part of that methodology is understanding how to model the frequency response of power converters, because to stabilize them you need to know their frequency response. And I'm going to present today some techniques which can be used and give some examples of typical power converters and how we can go about then stabilizing those. And also at the end, it's very important to measure control loops in practice, because the models you put together may not be accurate or may only be accurate over certain frequency bands. So ultimately, when you get your power supply up and running on the bench, it really is essential, in my opinion, that you actually measure the control loop and look at the phase and gain margins in practice. So they're the 3 main things I would like you hopefully to take away from today. So the agenda, I'm going to do a very brief refresher on control loop, as much as I can in a few slides anyway, to give you just some context for what we're going to talk about in today's webinar and why we would want to use closed loop control. Then power stage frequency response. This is quite a large part of today's presentation because it's something that in the past people have tended to find quite hard to do. There is documentation out there about how you can go about doing this, and there's a number of ways you can use. So I'll be talking in quite some depth about that. Then how do we go about closing the loop on those power stages? And I've split that out actually into 2 separate sections. Firstly, for non-isolated power converters, they're fairly straightforward because we don't have to worry about an isolation barrier. But if you do have an isolation barrier, that changes things quite a bit because you have to pass feedback signals over the isolation barrier. So the approach for those 2 is rather different, and I'd like to describe the differences there in these slides. And then we'll finish off with practical loop measurement with some examples of 2 ways we've gone about measuring a real converter on the bench, along with some actual practical measurements for you. And then we'll do our summary and questions. So hopefully that will be useful for you today. So closed loop control, for some of you this might be a bit basic, but I thought it's important to put some context and background to what we're talking about today. So firstly, if you think of a power converter as essentially a block that has an output, it might be an output current, it might be an output voltage. That output current or voltage is a function of many possible different factors. It's a function of your control demand, it's potentially a function of your input voltage, it's potentially a function of load current, temperature, and even as components age, the power stage behavior will change. So we're going to be modeling the power converter as possibly having multiple effects of all sorts of different things. And the aim of closed loop control is it allows us to control the output to be fixed to a predetermined reference level here, largely irrespective of the unwanted disturbances you have coming in. And that's really what closed loop control is at the very highest level. We can minimize the influence of all the unwanted elements and just control the power supply to provide the particular characteristics we want. Now, the way we go about doing that, hopefully you can read my my handwritten scrawl here. The way we go about doing that in a closed loop system is this power stage here has a gain. And I've used the term P of S because we're going to be talking about S domain or Laplace characteristics in terms of the frequency modeling here. Now, if that power stage gain is very high, you can see here that actually if that power stage gain approaches infinity, then the output voltage pretty much follows the reference voltage. The error signal is tiny in that case. In fact, in the limiting case, it's 0. So that's how closed loop control works. We make sure we have a very high gain here in the system, and then the output follows the input largely irrespective of the other disturbances. However, oh, sorry, that's exactly what I just said here. So if the power stage gain is very large, changes in V out due to the other system disturbances, they really only have a tiny effect. However, this is where I was coming to. You need to make sure the system is stable, and there are certain requirements on the feedback design that if you make this gain too high or it has the wrong gain and phase characteristics, then if you were to close the loop on it, it would actually oscillate, it would become unstable. And effectively designing your analog control system is the process of designing that model to be stable and give you the characteristics you want. So we'll launch question 1 at that point, please, Jose. Okay, so from a conceptual level, how does this work? Well, if we have an increase in the error signal here and the control input to output voltage has a positive gain, then a small error here, a small positive error here would become a larger positive error, and it actually gets subtracted then on the input side, and that reduces the error signal the next time round effectively, and the system is stable in a very basic manner. So that's why negative feedback generally is how we go about stabilizing the system. Oops. However, if our power stage response here inverts the error signal, so if an increasing control input results in a decreasing output voltage, we essentially turn that negative input into a positive input, and we get positive feedback. So a small error here turns into a bigger error by the time it's added on here, and that causes then a bigger error, and we get instability, and the system just falls apart. So we need to be careful that we have a certain characteristics in the power stage gain that it doesn't invert the signal. However, if the gain of the power stage is less than 1, then actually that inversion doesn't really matter, because even if it becomes additive here, when it goes around the loop and gets inverted, if the gain is less than 1, then it adds on a smaller amount each time, and the error signal decays over time. So the way to think about that in terms of the control or the world of control theory, that's the same as saying that if the phase shift of that power stage block must always be less than 180 degrees if the gain is greater than 1. 180 degrees phase shift essentially is inversion. So if we have inversion and gain is greater than 1, we have instability. So that really is what we're doing in designing the control loop, is making sure that this frequency response through the loop is less has a gain or a gain, or if the gain is greater than 1, we have a phase shift of less than 180 degrees, or if the phase shift is greater than 180 degrees, we must have a gain of less than 1. And that's really what our job is in designing this closed loop system. And the other thing to say here is that the gain and phase of that power stage and the compensation response, they're both functions of frequency. So as we go up in frequency, the gain and phase shift is changing depending on where poles and zeros are, and we use Bode plots to assess that stability. And they can become quite complex expressions to model, but essentially that's what we're trying to do, is we're looking at gain and phase through the loop as we go over frequency. So in that previous slide, I showed you just the power stage there, and we talked about the need to have that power stage gain as being very high if we want good closed loop behavior. Well, what if our native power stage gain is not very high? Well, in that case, what we actually do, we still have the power stage there, but we put an additional frequency dependent gain block in here that gives us that high gain that we want, especially at DC frequency or low frequencies in DC. And that's our control response. We add in this additional gain blocks to increase the loop gain and tune it for a stable loop response. And that's the compensation. So if you look into sort of classical control theory, people will call it a compensator or all sorts of different things. It's essentially, it's a frequency dependent gain block. And that's what we're designing when we're designing our control circuit, is the frequency response of that block. Now, in terms of stability, we now need to look at the product of the control and the power stage. So the loop gain now is not just the power stage, it's the product of the control, C of S times by P of S. And we have to apply that those stability criteria to that overall loop gain now. So our methodology in stabilizing and designing our control loop and getting a stable system has got 2 steps. Firstly, you need to know what the power stage response is, because otherwise you can't control the design response here. So firstly, we need to know the power stage response, P of S, for a given set of conditions. Then we will design the required control response here to give the overall loop gain that we want to provide a stable system and high gain at low frequencies, all those sorts of things. And that's the methodology, really. It's a 2-step approach, and it sounds quite simple, but actually there's a fair amount of work involved in doing those 2 steps. Before we go into the details of those 2 particular steps, it's good to start with an idea of what sort of a loop gain we actually want in our system, what sort of characteristics. We know we need it to be stable, but what else do we want that loop gain to look like? So this is an example from, it's actually modeling a flyback converter in closed loop. And I've just put this up here to give you a bit of an idea on what we're looking for in a gain and phase characteristic. So firstly, if you look at the black trace here, this is actually the overall loop gain for that flyback converter running in closed loop. The black line here, you can see as we go down in frequency, the gain's going higher and higher and higher, and that gives us excellent DC set point accuracy. Theoretically, if you just look at the math side of this, we would have a pole at DC which gives you infinite gain at DC. However, you have limited gain bandwidth product in op amps and things like that, so that gain actually does tail off at a certain point. But ideally, you want to have a gain characteristics which is increasing nicely as we go down in frequency here. We also want to cross over. So by crossover frequency, that's the frequency at which this loop gain crosses the unity gain point, or unity gain is 0 dBs. So that's here where you can see my marker. And we want that crossover frequency to be as high in frequency as possible, because that gives you a much faster transient response to disturbances in your system. So we want good high DC gain. We want high frequency crossover as well. The other thing is, when you do go through crossover with your loop gain, ideally you want to be falling at about 20 dBs per decade. So it's a first order characteristic here. And the reason you'll see actually in some later slides why that's quite important, but you can see here there's some gain peaking due to the power stage behavior. So we don't want those peaks to have any chance of bringing the gain back up and recrossing the 0 dB line. So if you've got a nice 20 dBs per decade roll off, you can say that the system is, there's no conditional stability issues there. It's a nice, stable, robust control loop. And there's a couple of definitions. Phase margin, you're probably very familiar with this. The phase margin is how close we are to 180 degrees phase shift at that loop crossover, the unity gain point. We typically target a minimum of about 60 degrees, or 50 to 60 degrees is reasonable. Oops, sorry. And the gain margin, that's actually how far below the 0 dB line is at the point the phase shift hits 180 degrees. So that's how far away we are from being an unstable system, if you like. And a typical metric to use there might be about 10 to 15 dBs, perhaps a little bit more if you're looking at a very robust system. But they're the sort of things we're aiming for in our control loop design here. Okay, right. Power stage frequency response. This is there's lots of ways of looking at this, and I thought the best way to describe power stage frequency response is to use a real example, a buck converter here, and this is going to be something called a voltage mode buck converter, running from a typical 12 volts input to a arbitrary 5 volt 2 amp output with a 100 kilohertz switching frequency. And this is the power stage that we put together in Plex to model that. So you can see the MOSFET diode and the output filter characteristics. What we need, remember, from that power converter, or sorry, from that power stage response, we need an analog representation going into the block, a demand signal going in, and some output signal like our Vout voltage coming out. But the actual power stage itself, the switch, needs a switching signal. So to generate the switching signal, we also include a modulator. And in a voltage mode feedback system, that modulator is typically achieves its behavior by comparing the demand signal coming in here, where my mouse is, to a reference high frequency sawtooth waveform here. So if we're running 100 kilohertz, you would have on this comparator inside the modulation block on one pin, you would have this sawtooth going up to a V peak value, and then we'd have the demand signal coming in on the other pin. And the output of that modulator then, the output of that PWM comparator becomes the modulated switching signal, which is going to the MOSFET. The example I've shown here, or I've tried to show here, shows an example of about 75% duty cycle, where the demand signal is 0.75 times V peak. Now, if I draw what that is, so if the demand signal is equal to where that red line is there, you can see here that we would get an output modulation waveform, as shown here, about a 75% duty cycle. If the input demand signal were to increase further, the duty cycle increases. And conversely, if that input demand signal falls, the duty cycle will fall. And there's a gain term associated with that as well, and we'll cover that on the next slide. So could we launch poll number 2 there, please, Jose? Thank you. So we need to know what the dynamics, the frequency response of that power stage is from that input through to the output. So let's take that same example, and let's take an example of where the modulator block gives 0 to 100% duty cycle with a 0 to 1 volt input coming in on its input here. If we do that, and then we step the demand from 0 at the start of this up to 0.41 volts to just over 600 microsecond time point, you can see here, as soon as we put that step demand in on the input, then the output voltage starts to rise. And actually, the reason I've chosen an input demand of 0.41 volts here is that results in a duty cycle, which gives us the 5 volts we want on the output of this converter when running from a 12 volt input. So there's a few things to note. Firstly, in steady state, you can see here that we have that demand of 0.41 volts DC going on the input. When everything has settled down, we're producing a steady 5 volts on the output. So we can say that the DC gain of that converter block is about a factor of 12 or 22 dBs. It's actually equal to 5 volts divided by 0.41, which is times 12. So that has a DC gain of 22 dBs. There's also, when you first hit it with that step demand, you can see that there's a second order response, or at least a second order response here. The output voltage overshoots slightly, and because we've hit it with quite an aggressive step here, we're actually seeing the natural dynamics of that power stage, and it's a second order response here. So there are some frequency dependent dynamics we need to model here, as well as the DC gain. The last thing to say is if the switching frequency is very much greater than the frequency that those power stage dynamics occur at, then essentially you can also ignore the high frequency ripple. And that's one of the fundamentals of one of the approaches we're going to be describing in a moment, and it's the small signal averaging approach. I put this last point on here. Obviously, you wouldn't want any real converter to overshoot that excessively. You know, we've got an output voltage going beyond 6 volts here. So normally what happens when you start a converter is you have a soft start period, but that's really outside the scope of what we're talking about on today's webinar. But in practice, you would have a nice controlled ramp up to its normal steady state operating point. So let's take a look at our averaged model for this buck converter. The way the averaged model works is it uses a small, or it represents that switching waveform here. The switching waveform is the voltage across the diode here. So that's going from 0 to 12 volts at 100 kilohertz. So it's generating a square wave. And what we're doing in the small signal modeling for this buck converter is we replace that square wave by a DC value, which has a DC value equal to the DC value of that square wave. And this becomes a bit clearer when I describe it in the plots here. So this switching waveform here, VSW, that's the switching voltage here. You can see it's going from 0 to 12 volts and then back down to 0 volts again. So we have an on-time T on and a switching period of T, and the duty cycle is T on divided by T. So what we actually do here is if we take the average of that switching node voltage, it's just the input voltage, which is 12 volts, multiplied by the duty cycle, which in our case here, when you look at the behavior of the modulator too, we actually have an average value presented to that filter network equal to V in times the demand divided by the V peak. And the V peak is the peak of our sawtooth reference in the modulator. So that means we can actually redraw our switching circuit that I've shown here with an averaged model. And this is what the averaged model looks like for that same circuit. So you can see that the output side of this is the same. The L1, the C1, and the R1, they're exactly the same. But we've created a DC source, which is just a mathematical representation now of what the demand signal is, and this is just how it's modeled in Plex. But essentially, we've taken out the high frequency stuff and we've turned this into a low frequency or DC model or small signal model. And when you look at this averaged model, it accurately replicates the dominant power stage dynamics, and it removes the high frequency ripple behavior, because the high frequency switching ripple doesn't impact the low frequency behavior. And if you compare those two models, the one at the top is that switching model I showed you in the previous slide. So it's actually got the switching ripple, which you can see on the inductor current there as a little envelope. If we then replace that model with the average model and do exactly that same step demand on the input, you can see here the average model follows the switching model very accurately, except we just don't have the switching frequency on there. So that means this actually is behaving at low frequency in exactly the same way that the switching model is, but we can actually now analyze this properly and come up with a frequency response behavior. Okay, so frequency response behavior of that particular model. Let's take a look. So in this particular converter, it's quite the buck converter is quite a nice one, because you can just inspect the behavior of that and literally write down the transfer or the complex transfer characteristics of this using the fact that it's essentially a complex impedance potential divider. Sounds like a bit of a crazy thing, but it's not too bad when you think about what it really is. And again, hopefully you can read my handwritten notes here. If you were to take inductor L1 and just rotate it through 90 degrees, you would end up with this circuit here, which I've shown where my mouse is. So actually the output voltage in the S domain can be represented as a potential division of C1 and R1 in parallel, and then L1 being the top end of the potential divider. And then you can work through all of this, and it's like a normal potential resistive potential divider, except that the impedances are now complex and they have a frequency dependent behavior. So if you want to work through all of that, you can do. Ultimately, what you end up getting is an expression where the output voltage is a function of S. So S is our small signal Laplace characteristic here, divided by the duty cycle of S. So essentially the gain of that stage is given by this expression. And I've put that here just to make it a little bit clearer so you don't have to read my handwriting there. You can see that we now get a frequency response given by this expression that you can see in the yellow. So you can see, firstly, we've got a DC gain term, which is the V in divided by V peak. And remember, for us, that's V in is 12 volts and V peak was 1 volt. So that gives us our factor of 12 or 22 dBs. So the DC gain works. And you can see we have a second order response here, which again ties in with what we saw from that step response I showed you on the previous slide. And the position of the poles and zeros, sorry, actually it's just poles in this expression, they're governed by the relative values of L1, C1 and R1. So again, now we've got a nice mathematical representation of that system. It's a second order response with a DC gain of what we'd expect to see. And if we plot that out over frequency, what we start to see is the frequency response of that power stage all the way from demand through to the output voltage. So we get a nice DC gain of 22 dBs. We have a pair of poles at roughly the resonant frequency of L and C. And then we have a 40 dBs per decade roll-off, which is characteristic of a second order system. So you can see here, below those pole frequencies, we've got largely 0 degrees phase shift. Then we have 2 poles to end up getting 180 degrees phase shift. So that's all fairly classical sort of control theory, but it ties it back to that power stage, which is a great thing for us to be able to then use to go about modeling the control response. Yep, I think I've already mentioned that part. So in terms then of how we can go about modeling this, I've shown you an analytical way for the buck converter. You can literally write, almost by inspection, you can write down the frequency response. However, the buck converter is a particularly easy one to work on. For some of the more complex topologies, it can be difficult to come up with that small signal response. So in those cases, you can actually use simulation tools, and they will give you the frequency response. The downside of doing that is you don't have the basic equations to understand how parameters play against one another. But sometimes it can be a useful thing just to do it in simulation, or there are other techniques as well. The example I'm going to show you here is that same buck converter, but in the Plex simulation software, we can put that buck converter essentially into a system whereby you have an input and an output. So the output here is our output voltage. The input is the demand going into our modulator. I've added on a DC offset because we need to move it up to a certain DC operating point to make it work properly. But essentially, we've got this Plex circuit here, and then the Plex simulation software will sweep frequency over a specified range and look at the loop gain as a function of frequency, which essentially is what our Bode response is, and that can be quite useful. It works okay. We found up to about 1/4 of the switching frequency, and then it starts to fall apart. But if I show you the comparison between that analytical model and the simulation model, you can see that actually it's very useful. So the plot at the top of the screen here shows the results from that automated sweep in Plex, which is actually a full switching model of the system. And you can see here we've got the same roughly 22 dBs gain down at low frequency. We have a pair of poles sitting at around about about 6 or 7 kilohertz, something like that. And that compares very favorably with the averaged estimate model, which was a result of that complex potential divider I showed you. So this is actually great. It allows us a very simple way to simulate if we want to as well. We'll launch question 3, please, at that point. Okay, so we've got our nice way, or a couple of ways of modeling the power stage frequency response. Now we want to go about closing the loop. In the lead up to this webinar, I actually put some information out on LinkedIn about a document we wrote, which basically highlights all the different types of control you can come up with for analog control. if you want a link to that, put a request up in the chat box, and we can email this to you after the webinar today. I've put a few pictures from that document here just to give some context, because we're going to use the results from that document to help us design our control loop for our buck converter. So there's three types of control we talk about. There's type 1 control, type 2 control, and type 3 control. They're fairly standard in the industry. Type 1 control is shown here, and it's often known as integral control, because all we have is a single pole at DC. And if you implement that in an analog circuit, it's just an integrator circuit, as shown here. And you can work out the S-domain representation of that. If you plot out the frequency response, gain, and phase, you can see here that we have a behavior which is almost close to what we want. You know, with a pole at DC, we have a nice high gain down at low frequencies. We can choose the unity gain crossover frequency by choosing our values of R1 and C1. The only downside of type 1 control is that we have a constant fixed 90 degrees phase shift, but it's very simple to design, that one, and it's often what we use to stabilize, or we can use to stabilize converters. If we're really not sure about their frequency response, you can design for a very low loop crossover frequency, and you should be able to come up with a stable system. The only downside of this, as I mentioned, is it can require a low frequency loop crossover, a low or a slow loop response, and that's primarily due to this fact that we've got this constant 90 degrees phase shift through here. So we need to cross the loop over well before the dynamics of the power stage start to come into play. Otherwise, we can end up with an unstable system. So it's very simple, but it can end up being quite a slow control system. Type 2 control, we still have the same pole at DC, so you can see here the gain characteristic is increasing as we approach DC, but we've got an additional 0 and a pole now in our characteristic. And the way we implement that in a real circuit is here. We've got the same op-amp circuit, but we put an additional capacitor and resistor in parallel with C1 here. And there are various different ways you can go about placing these poles and zeros, but the key thing here is if you look at the phase response, obviously down at very low frequency we have that pole, so we have a 90 degrees phase shift, the same as type 1 control. But with clever placement of the 0 and pole here, we actually get a reduction. The phase shift close to crossover can be reduced, well, theoretically almost to 0 here. So this allows us to improve the performance of our converter by the fact that we don't have so much phase shift at crossover. The price we pay for that is we actually end up reducing the DC loop gain a little bit as a result. However, this is quite a neat technique to allow us to increase the crossover frequency of a converter, where the 90 degrees phase shift of a type 1 control would be something that would cause us a headache. So 2 poles and 1 0. The phase lag due to the compensation can be reduced to almost 0. And this is probably this is a very commonly used approach. It's used all the time for power converter control loop stability. So it's definitely one worth studying and getting used to. Type 3 control, again, we're taking a step further on now. In type 3 control, we have 3 poles and 2 zeros in this characteristic. So we still have a pole at DC because we need good DC accuracy. Then we have 2 zeros. Often, well, it depends on the methodology you use to design them, but often they're placed at the same frequency. And then we have 2 poles at another frequency here, and we aim to cross over where the mouse pointer is now, roughly in the middle. The benefit of type 3 control is we can actually introduce some phase lead at crossover. So remember, with type 1 control, you always have 90 degrees phase lag, essentially, through your compensator. With type 1, you can get that almost to 0 degrees. With type 2 control, you can get that to almost 0 degrees. And with type 3 control, you can actually introduce some phase lead into the system. And you do that by adding a resistor and a capacitor across. Well, this is the implementation we use here. In the op-amp circuit, you add an additional resistor and capacitor here in parallel with the upper resistor of your feedback network. And with some simplification, you can work that through. And that can, again, become quite useful if you're really trying to push the limits of your crossover frequency, because you can tune the phase boost here to give you some benefit to allow you to push that crossover frequency a little bit higher. It is actually often used for voltage mode buck converters because they have that double pole characteristic in the transfer function of the power stage. You know, that double pole pair in the power stage will always give you 180 degrees phase shift. So you need to stop. If you really want to cross over at high frequencies, you have to do something about your phase in that system. When you use other controls, other methodologies like peak current mode control, for example, you don't have that complex pole pair to deal with anymore. In terms of then choosing the locations of those poles and zeros, there are multiple different ways you can go about doing that, and everybody has their own preferred methodology depending on what they're trying to achieve. I'd like to describe briefly one approach we use here, and it's based on actually fairly traditional approaches. It's called the K-factor method. I've put a reference up here on the slide. This is quite a useful document by a company called Venable Industries, and they produce feedback response analyzers. And some of the theory they've put down quite nicely describes how this K-factor method works. So if you think about the type 1, 2, and 3 control schemes, type 1, we have the straight line of gain. In type 2, we have this sort of characteristic with a flat region. And type 3, we have this decreasing, increasing, and then decreasing region. So what we do is we define this factor K, which in type 2 control here, we place the frequency of the zero, a factor F, or F is your crossover frequency here, which is where you would originally cross your type 1 control loop over. In type 2 control, if we place the zero at a frequency F divided by K and the pole at a value of K times by F, that's how we go about placing those. And the value of K then is a factor which determines the amount of phase boost. So this graph here again is from this paper that I've described. With type 2 control, you can see here we can plot out the boost, the phase boost you get, so in degrees, as a function of the K factor. And therefore, if you go for a big K factor, which means that pole and zero are effectively symmetrically placed around F, but a long way away, then you can have a lot of phase boost, but you degrade your DC gain more. And it's that value of K that allows you to trade that off. In type 3 control, you place the poles and zeros as shown here. And in the K-factor method, it actually places the two zeros at the same frequency and then the two poles at the same frequency, but the other side of crossover. And again, if you do that, you can plot out for type 3 control the amount of phase boost you can get as a function of that same K-factor. The reason I quite like that methodology is it really gives you a consistent way to place poles and zeros depending on the amount of phase boost you're trying to achieve. So that's why I'd recommend getting familiar with that approach. But there are other ways of doing this as well. The key thing, again, all of those responses have a pole at DC, which is essential for good DC steady state accuracy. Okay, we'll launch question 4 at that point, please, Jose. Okay, so closing the loop, non-isolated. So this is pretty much what I've shown you in the previous slides. Let's take an example of our buck converter again. We know what the frequency response of the power stage is here. We've already ascertained that. We need the loop gain to cross over before that loop phase moves to a total of 180 degrees. So for the first look at this, let's just use simple type 1 control, the pure integral control, because it's just a simple way to stabilize this system. Now, if you look at that integral control here, you can see that we get the frequency response, or the estimated frequency response, is given by what you can see in my notes here. The reason I've drawn it out like this is where are we? Yeah, here. I wanted to explain that this circuit here essentially gives us this loop characteristic here. So this loop characteristic, we've got the power stage gain, which is the same as what we had before, which is the part in yellow here. We've got this factor of 1 upon S CFB RFB1, and those values relate to the values you can see in the circuit here. But look in the circuit here, when you actually work out this characteristic, there's a negative term here, and that's how this circuit implements the subtraction block for the error amplifier. So really what I'm trying to do is relate that circuit back to a loop gain representation of the whole system here. So that minus is how we implement that error term. There's also a term here on the front end, which is just a DC term, because we have the reference voltage here, which I think in my application example I've used as 1 volt. The actual output voltage, the set point, is then going to be governed by the potential divider of RFB1 and RFB2. So we have to include a block here to give us that correct reference point. So this is just a map. This representation where my mouse is just a mapping of this circuit into a closed loop representation. And again, we're getting constant 90 degrees phase shift through the control block. And we want to target, let's take a target for crossing the loop over at 1 kilohertz, because that 1 kilohertz is nicely down here on the Bode response, well before the pole pair of our power stage. So let's try and cross the loop over down at 1 kilohertz. Let's do that here. So at 1 kilohertz, we know the power stage gain has 22 dB, or the power stage has 22 dBs gain, which we found both from our mathematical analysis and from the Plex simulation. So if we want to cross the loop over at 1 kilohertz, so the loop here is the blue trace. If we want to cross the loop at 1 kilohertz, we need to make sure that the compensator response, that integral control, has a gain of minus 22 dBs at 1 kilohertz, because when you sum those two together, the overall response then is just 22 plus 22 dBs for the power stage, minus 22 dBs for the control, giving us 0 dBs for the control loop. So let's do that for our system. We know that minus 22 dBs is 1 upon 12, and we want the frequency domain response at 1 kilohertz for our integral control to therefore be equal to 1 upon 12, so minus 22 dBs. And that has to occur at a frequency of 1 kilohertz. So here we can replace S with 2 pi f, where f is our target crossover frequency. And therefore, if we manipulate that equation here, we get a product RFB1 times CFB1 is equal to 12. Well, it's equal to this expression you can see here. That gives us a value of RFB1 and CFB1 multiplied together of 1.91 times 10 to the minus 3. So you could come up with any combination of resistors and capacitors to do that. I tend to choose the capacitor first, because it's much easier to use a standard capacitor value, and then you've got more granularity in your resistor values. So let's choose 100 nanofarads, for example, for our capacitor CFB1. Using this equation, that gives us the RFB1 value of just over 19K. And if we want also the 5-volt output, remember we had this potential divider behavior. You have to actually choose RFB2, that's like a bias resistor, to give us the right output. And with an RFB1 of 19.1K, we need about 4.78K for RFB2 to give us a nice 5 volts output. So let's take a look at modeling that. So we can, again in Plex, we can model the closed loop behavior of that power stage with the compensation we've just designed here. So you can see here, this is the power stage I had before at the top of the screen. We've got our modulation block as before, and we've got our error amp here. This is our op amp. So here is our 100 nanofarad capacitor. Here's our 19K capacitor, and here's our 4.75, 4.78K resistor to give us the right output. And then we've got a 1 volt reference for our feedback. And that's just arbitrarily chosen. So if we use that system and actually do that same AC sweep in Plex, what we end up getting is this characteristic, which I'm showing you here. So this is directly from the simulation. So this is the loop gain of that closed loop system when it was operating in a stable manner. You can see we are now crossing over at about 1 kilohertz, which is exactly what we designed for. The phase margin here is quite large. It's about 90 degrees because we've been quite careful to cross over at a low frequency. However, you can see here that as soon as we get close to that double pole pair of the power stage response, the phase is diving off a cliff. And the phase, and then the gain margin, which is the point at which the overall loop gain phase reaches 180. we've only got about 8 dBs gain margin. And in a moment, I'm going to show you why that really isn't going to be enough for this system. But at the moment, under this simulation, it's stable in steady state. So you can see here, if we start simulating, this is the switching node voltage here. So again, the voltage across the diode. And this is the output voltage here, which you can see is almost exactly 5 volts. So we've got a nice controlled 5-volt output, and the system is stable. It's operating in closed loop control. So everything looks good there. But again, integral control is good, but it is going to result in a slow loop, and there are some other challenges with the voltage mode buck here, which I'm going to show you in the next slide. Oops. Before that carries on, I've got a nice video here. I was going too fast there. So this is that same video, that same simulation in Plex. And what I've done here, the great thing about simulating in Plex is you can set a simulation running, and then in real time you can type in a new value for your different circuit components. So what I'm doing here in my simulation and the video I'm going to show you in a minute is what impact changing the capacitor value here has on the time domain response. So you can see here, before I start the video playing, what I've actually done here is I've put a step load on the output of this system. So normally it's running at 2 amps, that's the design current point, but here I've put a step load in. So it's the output current demand from this converter is changing from 1 amp to 2 amp. And I think it's doing it at about 100 hertz. So we have 5 microseconds at 5 milliseconds at 2 amps, 5 milliseconds at 1 amp, and so on. And by doing that step response, you start to get a feeling of whether there's any instability in the system. And the reason I'm doing that is I want to show you the impact of playing around with the compensation response, which we know will affect the small signal gain. I want to show what impact that has on the transient behavior here. So I'll stop this video at points as we go, if I can get it going. Oh, hang on, I'm wrong. Yeah, I think I have to do it here. Yes, there we go. So you can see it's running nicely now. Now, if you look where my mouse is, we're going to change the 100 nanofarad cap to 10 times higher. So you can see here, if I pause, it's stopped. I'll just have to pause the video at that point. Here we go. So you can see now that we've gone to, in fact, I might be able to just bring the video back a little bit. Oh, it's not going to let me. Okay. So you can see here I've increased to a 1 microfarad capacitor here. And by increasing the capacitor, I've lowered the loop crossover frequency here. And what you can see here is now it's actually, when you put a load transient on here, this is the output voltage of that converter. It's taking longer for the output voltage to move back to its design set point compared to what it was when we had 100 nanofarads. So if I leave that going, oh, here we go. It's going again. So this is with 100 nanofarads. I'm going to step now to 1 microfarad. So look at the response now. You can see it's gone to 1 microfarad, so it's slower. I'm also going to reduce that capacitance below 100 nanofarad. Oh, that's up. Sorry, go 10 times higher. So this is at 10 microfarads. You can see now that the output doesn't have chance to recover within the 5 milliseconds, and we're starting to get a very, very slow system. If I then bring that back to normal, you see we have a fairly fast response. But let's take that capacitance value even lower and take it down in steps. We'll start with 80 nanofarads. You can see we're starting to get a slightly more oscillatory behavior when the transient event occurs. So down at 70 nanofarads, watch the behavior as we take it down even further. Okay, that's 60. You can see here it's starting to, it's on the borderline of being unstable now. And if we take it even further down to 50, we actually end up with an unstable system. And you can see here that under the light load condition down at 1 amp, we've actually got instability in the system. And if we do a zoom of that, you can see there we've got classic instability now in the closed loop system, because we've not, well, we played around with the frequency of that integral control to the point whereby the loop gain is just not stable anymore. And the reason that happens here, so this is the feedback capacitor down at 50 nanofarads. So this is essentially increased our loop gain. Remember, we were crossing at 1 kilohertz before. When we had 100 nanofarads, we were crossing that loop over at 1 kilohertz. By reducing the feedback capacitor now to 50 nanofarads, it increases that whole integral gain. And the problem we get, and this is why you have to be a bit careful with conditional stability systems, is the red trace here is the frequency response and the gain when we had that 2 amp load on the converter. So it's just about stable here with 50 nanofarads, which is what we saw under the transient conditions at the top when we had the 2 amp load current. However, when we take the loop, take the output load down to 1 amp, you can see the loop gain now becomes more peaky here. In fact, you can see it on the yellow trace. The loop gain becomes more peaky, mainly because that LC combination in the buck converter is less damped, so you get more peaking around the point where those poles are. And in the case here where we took that feedback capacitor down to 50 nanofarads, that peaking of the gain means that where we thought we would be crossing over, actually the gains come back up. And remember, the condition for stability is we must have a gain below unity when we have a phase shift of 180 degrees. Phase shift of 180 degrees is where my mouse is now. So if we trace that back up, you can see that the gain is greater than unity, and that's why we have instability. We could do that with type 2 control as well if we wanted to. Actually, this is type 1 control. There's an error in the title there. We can reduce the loop crossover at 100 hertz and stay with type 1 compensation. So if we, rather than crossover at 1 kilohertz, we design for that 100 hertz crossover. That's the same as when in that simulation on a couple of slides ago, I showed you the response when we changed the feedback capacitor up to 1000 nanofarads. That gives us an unconditional stability in the system now. It doesn't matter the fact that we get peaking effect in our power stage under light loads. We still get a nice, well-controlled system, but it's a lot slower. You could go ahead and design type 2 or type 3 compensation to improve that further if you wanted to. Okay, so just moving on to sort of finish this section off. Briefly to look at isolated control. It's a bit more complex because you have to introduce normally an optocoupler into the feedback network. And what you can see on the screen here is a fairly typical generic feedback scheme used in an isolated converter. So we have an optocoupler here. With the way an optocoupler works is that the current on the output side is the same as the current on the input side multiplied by the current transfer ratio. This is uses an LM431. In fact, I'll just click through here. The same methodology is used as before with the non-isolated approach, but the feedback obviously has to be isolated, and it uses that optocoupler. The reason it's more complex to model is there are now multiple poles and zeros you have to think about in this system, and not depending on how you implement it, not all of them will be there. One of the key things that you have to be aware of with an optocoupler feedback design is this optocoupler output capacitance here. The optocoupler itself has a limited frequency response. Effectively, you can model that as having an output capacitor, which is what we're modeling with C4 here. That means that the bandwidth of the system when you're using optocoupler feedback is really going to be driven by the frequency response of that CTR or the output capacitance of that optocoupler. It also, the optocoupler CTR here, because it's directly in the feedback loop, that affects the DC loop gain. An opto CTR can vary over quite a wide range. So when you're using optocoupler feedback, it is really important to have good phase and gain margins to counter aging effects on the opto, which can change the CTR and things like that. To model this, you can do it analytically. We've just put it all into a MathCAD sheet to model the frequency response, and you can just type your values in, and you get, at the moment here, it's an example which shows a typical response which looks a bit like a type 2 response. You can see we've got a pole at DC, we've got a 0 around this point where my mouse is, and then we've got a pole here, and you get the phase boost that we saw before from the K-factor design. But there are multiple ways of designing that. But you can normally, it's a good idea to model that in MathCAD so that you know exactly what's going on in your feedback system. You might be wondering where the error amplifier is in this system, and it's this thing called the LM431. An LM431 is a 3-terminal device. It's called a shunt regulator. But when you look inside the datasheet for that part, it's essentially an error amplifier with an output transistor and a reference all in one package, and they're available in a few different flavors. Very commonly used is the 2.5 volt reference. That's essentially what that models our error feedback system here. So this might be on the output side of an isolated power supply. So actually the error amplifier part, the part that's comparing to a reference, that function is performed on the isolated side, and the signal you pass back across to the primary side of the converter really is just the error signal. And that's important because remember, if we were to try and pass back an accurate representation of the output voltage itself, we'd have to worry about the accuracy of the CTR value. Whereas if we do the comparison on the isolated side and just pass back the error signal, well, the CTR just plays into our loop gain. It doesn't give us any accuracy problems. So that's a very typically used approach for an isolated control. Again, very briefly, I wanted to mention this before the end of the webinar. There is a technique which it can look quite intimidating and complex mathematically at first, but it's a very powerful technique for modeling all sorts of different power converters, both in discontinuous mode and continuous conduction mode. And it uses state space approaches to create matrix representations of those power converters in sort of the average steady state condition. And as an example, a SEPIC converter here is a converter you may have come across before. It's actually a fourth order characteristic, the SEPIC converter. So it becomes something that's quite difficult to model purely analytically. However, using state space approaches, you can arbitrarily model all complexity of converters really, and the complexity doesn't, or what would be complex for the analytical approach doesn't really cause the same problems. You've just got to become familiar with that approach. If you want to learn more about that, there's a fantastic book that I would recommend. In fact, this is one of the best books I think you can find on power electronics generally. If you take a look at this book, it describes how that approach works and how you can use it in all sorts of different scenarios. So I'd really recommend spending time looking at this technique if you're able to. We've done that quite successfully now on all sorts of topologies, and it's a great way for very quickly modeling the frequency response of all sorts of converters. Question 5, please, at that point, Jose. So we'll finish off now with some practical loop measurements. I promised these back at the start, and it's one of the most important parts of designing your power converter is making sure that the loop itself is what you expect it to be. So the traditional way we have gone about measuring loops is you imagine that buck converter I showed you on the few slides ago, where we have our integral control error amplifier here. What we end up doing is we put a small resistor, 10 or 20 ohms, something like that, in series with the high side resistor, and we couple a swept sinusoidal signal into that resistor to create a disturbance in the control loop. So really what we're injecting a disturbance in the control loop and then measuring the response of the control loop to that disturbance, which essentially, if we do that over frequency, that gives us our loop gain. The way we do that, we inject the disturbance here and then we measure either end of those two test points as a function of frequency. And you can do that fundamental measurement using multiple different bits of kit. The one I'm showing you here is actually, I'm very fond of this piece of equipment. It's rather old now. It's a very old network analyzer that we use for all sorts of stuff, but it's still one of my favorite pieces of kit. And the good thing about a vector network analyzer like this is it will generate the source signal for you, which you can see where my mouse is now, and then it will look at the two outputs to give you your phase and gain. The good thing about it is the way it works is it has a very narrow band. You can specify a very narrow resolution bandwidth, which essentially is a narrow band filter which goes around the measurement point. So it allows you to make very low noise measurements, and that gives you a nice, smooth, predictable phase response. So we use that network analyzer to inject a swept sinusoidal disturbance into that control loop whilst the converter's actually running. The network analyzer then measures the magnitude and phase shift, and that determines the loop gain in our system. the example here is, I didn't have that buck converter I showed you, but I did find an old flyback converter that one of our students once built. And that that flyback converter is a 24 volts DC input, and it delivers 30 volts at half an amp on the output. And I just wanted to show you a video of that measurement being taken. And I've actually sped this video up by a factor of about 30 because I was using a very narrow band resolution bandwidth, and it takes quite a while for it to do the measurement. So let's take a look. You can see the response going through here. So this is the network analyzer is just sweeping the frequency from, in the case here, I think we're going from 10 hertz up to 100 kilohertz. The yellow trace, if the colors come out okay, the yellow trace here is the loop gain, which you can see it's flattening off at low frequency, probably because we're running out of loop gain in the error amplifier. But you can see here, we cross over, in fact, this is the crossover point here. It crosses over about 450 hertz, something like that. And the phase margin at that point, you can see, is about 60 degrees. So that's a nice, stable control loop. And we have a nicely falling, a nice 20 dBs per decade roll off, which is exactly what we want. You get some funny stuff happening up at high frequency, because remember, this is measuring up to 100 kilohertz. We've actually passed through the switching frequency of the converter at that point. So the data out beyond half the switching frequency is largely meaningless. We're really interested in what's happening down at low frequency. In recent years, people or manufacturers have invested in developing time domain based approaches using oscilloscopes to try and do this same measurement. And this is quite good because the vector network approach can be quite expensive. You need a dedicated piece of equipment, and they're just more cumbersome to set up. So I wanted to also show you some of the capabilities of modern scopes to do this same measurement. The time domain measurements, obviously a scope is a time domain instrument. They don't have that same resolution bandwidth, that narrow band filter. They're essentially they're trying to pick out the low frequency content in all of the noisy signal they're receiving. So that generally means that scope-based or time domain measurements are always going to be more prone to noise and error. But we have interestingly found that results can be fairly comparable to the vector network approach. We've fairly recently bought one of these just out of curiosity to see whether the frequency response analyzer was any good. So the one we bought was from Rohde & Schwarz. It's one of their sort of entry-level low-end scopes, but they include this feature as an option which we wanted to explore. So let's take a look. So this is a video of that scope running, doing exactly the same measurement that I showed you a minute ago from the HP unit. Hopefully you can see the blue trace and the sort of orangey colored trace appearing as we go there. And at the top of the scope, you can actually see the injection signals or the measured signals that it's using to form the gain and phase. So actually that was that was real time as well. So it was much faster to do that compared to what we saw with the vector network analyzer. And the results aren't too bad. It actually predicts a loop crossover of 447 hertz and a phase margin of 61 degrees, which is almost exactly the same that we got from the vector network analyzer. So I was quite impressed by this, actually. It's a neat way to do a low-cost frequency response analysis of your converter. So definitely worth taking a look at. In terms of a data comparison, for that same flyback converter, we've got some MathCAD models that use that small signal average state space approach I described to you, and I wanted to just compare the predicted outcome of that in closed loop operation versus the HP 4195 and the Rohde & Schwarz scope-based measurement. So firstly, the small signal state space model for this particular converter predicts a crossover frequency of 450 hertz and actually quite a high phase margin of about 91 degrees. So this is predicting a very stable system. The measurement of the actual system on the vector network analyzer, we saw a crossover frequency of 457 hertz, so very, very close to what the analytical model predicted. But the phase margin's a lot lower. It's only 60 degrees compared to the 91 degrees that we were expecting. And then the scope measurement for comparison, we got a very similar crossover frequency, 446 hertz, and the phase margin, again, about 61 degrees. So the conclusion there really is that the crossover frequency prediction is very close, but the phase margin is still adequate in the measurements, but it's lower than what we expected from the analytical approach. And that really is to aim to illustrate the importance of doing practical measurements. If you just base your work on even quite a complex small signal model, the accuracy of that model depends on how good your model is. And it's very difficult to model every little last part of a control loop, especially when you've got multiple factors like the power stage, your compensation, optocouplers getting involved. So you really do need to take time to take real measurements and just check and validate your theory and make sure it's looking good. But in this case, the results aren't bad. So we'll launch question 6, please, at that point, Jose. Thank you. So just in summary, we're just finishing off now. Stable loop design, it really requires knowledge as a starting point of the power stage frequency response. If you don't have that, it's going to be very hard for you to make any, or to have any methodology for designing a stable system. I'm a big fan of the small signal average state space approaches because once you get the hang of how to do that, you can use them to model all sorts of fairly complex topologies, which are just, they're next to impossible to model analytically, or very complex to model analytically. So if you're looking to invest time in learning how to model power stage frequency response, become familiar with the average state space, and it's very well described in that book reference that I provided earlier on. And I think it's also true to say there are certainly many ways to approach the compensator design, and I've described the K-factor approach here, but there's all sorts of other ways of doing it depending on your particular preferences and what you're trying to achieve. So the K-factor isn't the only one, it's just the one I've described here. The key point, as I've stressed a few times here, it really is essential to measure control loops in practice to make sure that they really are robust, and measure at various different operating corner cases as well, because all sorts of different operating conditions can affect loop gain behavior. Good. I think we're just slightly over time on that, but I do hope that's been a useful introduction into analog control of power converters, and we'll move on to some questions now. Okay, so we'll take the question I've got at the top here. So this question is the setup for the time domain scope-based approach the same as the network analyzer? Do these scopes replace the Bode 100? Okay, that's a great question. So the Bode 100 is it's a dedicated instrument produced by a company called Omicron Lab, and there's a few companies around that make these. It depends what you're trying to achieve. The setup is the same. You still need an injection transformer, and we wound our own one here. You still need to inject that disturbance into the loop, so the scope generates that disturbance signal, and you inject it via the transformer, and then you use the scope probes to measure the 2 points in that loop response. So it's essentially the same setup. Whether it's a direct replacement for the Bode 100, I think the jury's still out on that one. I would say for basic measurements possibly, but the benefit of a system like a Bode 100 or an AP Instruments or a Venables system is that they are generally vector network analyzer based systems. So they have this nice narrow band resolution bandwidth filter that is there to give you a very accurate measurement. The problem with time domain based approaches is that it's very hard for the scope to make a really accurate measurement when the signals it's measuring have got so much inherent high frequency noise, wideband noise on them. So whether they replace the Bode 100 is really a subjective question. I'd say probably not, but I would say at the same time it's worth having time domain based capability in your arsenal of stuff to do, because if you get the time domain and the vector network analyzer stuff comparing well, then you're in a good place. And we've only started recently using the scope based approaches, and I've been quite impressed with them. They're not bad. So I can't really say they replace them. Is there any cheaper alternative? So next question, is there any cheaper alternative for measuring the loop gain, maybe with a sweep signal generator with a typical scope? I don't know really. You sort of need to automate it. It'd be very difficult to do that manually. I would say use a dedicated piece of kit for doing it. I mean, you could perhaps build your own, but I think it might be quite hard work to make it work very well. But essentially, if you wanted to do that, you're trying to essentially do what the Rohde and Schwarz scope is automating for us. It's just you have to make it work yourself. So it depends on how well you can make that work, really. Next question down, please. Will the MathCAD sheet or Plex models used for this webinar be available for download? No, they're not going to be available for download. If you the best thing you can do, and we get asked this question a lot, if you're really interested in learning about how to implement things in MathCAD sheets, that sort of stuff, especially the state space, average state space modeling, the best thing you can do is use the texts that I've shown you the references to and build your own, because in that process of going through the process of building your own sheets, it's painful at first, but you end up becoming far more knowledgeable because you really understand how the modeling techniques work. If we just make our sheets available, it doesn't make any sense, because people aren't going to learn by doing that. So the best thing to do is, again, look at what we've presented today and the references, and if you're really interested in developing that knowledge, then go ahead and build your own. So next one down, can you please share the simulation tool link? It looks interesting. I don't know if I can type or not. The tool set is from a company called Plexim, Plexim. In fact, I can probably type it. I'll type something here. Hang on, it's just moved. Okay. I'll just describe it. So that the company that sells that toolkit is a company called Plexim, Plexim. If you search for them online, you will find their webpage, and the tool they use is called Plex, Plecs, and it's a fantastic package for modeling power electronics. In particular, I really like that small signal modeling capability. The fact you can do a sweep for you. You can sort of do a similar thing in Spice, but I've tried to do it. It doesn't really work quite as well. Plex is very, very good for doing that. So hopefully you've got the reference to that now. If not, then just ping me a message. There's a next question down. What is the effect of increasing the bandwidth? That's a very open question. So one effect of increasing the bandwidth the way you increase bandwidth would be to increase the gain often. One of the effects of increasing bandwidth might be that if you get it wrong, your system becomes unstable. So it's something you don't want. So if you can increase the bandwidth of your system and maintain the stability margins that we described in the webinar, generally what you're going to achieve is a better transient steady state response. So remember when I was doing that step load in the simulation, if you increase your loop bandwidth and you have a stable system, it will recover from a transient condition much faster than it will if you have a very low bandwidth. So high bandwidth is great, but you've got to be careful to make sure it's not so high that the system becomes unstable. There's another question here. I was hoping someone might ask me this. So can we call this type as a PI control? So another way of going about loop design is something called PI or PID control, and that's something that's been around for a long, long time, and it's often used. It's got more of a background in system level design, like actuators and things like that, where you just don't know what the frequency response is going to be. So you actually there are PID tuning algorithms which allow you to design your compensator without you having knowledge of the frequency response of your plant effectively. And the way it does it is it starts with a very low loop crossover frequency, and you change parameters. For example, if you had pure integral control, that's the same as the type 1 control I described here. Excuse me. So historically, PI control is almost like type 2 control, where you've got proportional and integral control. There's an extra pole in type 2 control. So there is a lot of correlation between the two approaches. And when I was writing this webinar, I was actually thinking about whether to put in a few slides talking about the similarities between PI or PID control and the what you would typically use in power converter design, which is type 1, 2, and 3 control. And there are direct correlations there. As I mentioned, it's just almost like a terminology thing. So yes, you can actually use proportional integral control because it's almost the same as type 2 control. It's just the methodology of designing designing where the poles and zeros go effectively is different, but it's the same end result. So there's another question coming at the top. I'm using a D-Space data acquisition system to control the inverter. Is it possible to do frequency response with that device by Simulink tools? Whew, I don't know that system well enough to know that. You know, if you did want to do that, you would have to have some sort of real-time loop. I think a D-Space system essentially allows you the capability of controlling your hardware from a Simulink environment, if I understand it well enough. I think you should be able to just on your control input put a swept sinusoid signal and inject it into your DC operating point, and then look at your output. How you actually go about making that work in that environment, I can't comment, but it should be possible to do that, because all you've got to do is to put a swept sinusoid in on the front end and look at the response, and then compare the two in terms of gain and phase. So it should be possible to do that, I would think. I think that's all the questions answered today. Thank you very much for attending. I do hope it's been useful. And a week today, we're also going to have a further webinar to talk about digital control. So to expand on what we've spoken about today, but then to include factors like how do we actually implement this in a digital control algorithm. So if you found today's webinar useful, please register for our webinar next Tuesday as well. And we hope to see you then. Thank you very much. Bye-bye.